Ophthalmic surgery involves operating on semi-transparent structures, often with bright lights coming at you. So refractive surgery had to be good for ophthalmologists to want to have it on their own eyes. And the very fact that a very high percentage of ophthalmic surgeons have had refractive surgery, and those refractive surgeons are even higher, as you quoted, 60%, even higher are some statistics, and essentially they vote with their own feet. But the most vision critical people in society, particularly military, special forces, and also combat aviators, fast jet pilots, a very high percentage have refractive surgery, much, much greater than in the general population. So the paradox is that those who have most to worry about having their vision corrected are actually the highest users of laser refractive surgery. And I think that really is the answer. You're right, there has been a dramatic improvement in predictability. The original excimer laser corrections from 1990 in the research studies at Moorfields Eye Hospital, a -4 treatment had a 1.2 diopter standard deviation, a huge scatter. And then in 2002, 2003, when wavefront guided treatments came in with full objective measurements and wavefront sensing, that standard deviation dropped to 0.3 diopters. That is a huge statistical improvement in outcome. So instead of being unpredictable, as we used to describe it in the early to mid-1990s, there's now a high degree of predictability. And that standard deviation, that scatter, hasn't changed since then. There's some suggestion that femtosecond laser-generated LASIK flaps had a very slight improvement in predictability, but it's hard to show that statistically in terms of as a full scientific study. But that predictability is there because of a number of factors. Excimer lasers got better. The original lasers had a 40% variation in power output between the beginning and the end of a treatment, and that got reduced down now to just a few percent, around about 3%. We know that temperature is critical for femtosecond lasers, which are solid state, and we know that humidity is critical for excimer lasers. And the reason for that is that the excimer laser, when it hits oxygen, will knock off atomic oxygen and create ozone, and the ozone layer in the atmosphere, of course, absorbs ultraviolet. So the excimer laser pulses generate their own ozone and block their own beam. So having that measurement of humidity, which is now built into excimer lasers, or they have a nitrogen-filled cavity, has got around this issue. So they've got better. Surgical technique has improved. Surgeons, particularly experienced surgeons, know they have to be, to a certain extent, robots. They have to keep the same technique and not vary it, try and have the same timing, and they practice like any athlete to get that timing. So surgical techniques got better. And so with all of that, and essentially obsession in delivery and obsession with imaging and accurate measurements to put in, that's why we have the results we have now. The big unknown factor that we have with each treatment is corneal biomechanics. It's been talked about for 2 decades. Finite element models of the cornea have been built by Peter Pinsky at Stanford and others, and they're fascinating models, but we have no data to put into those models where we can vary for the individual and customize to the individual cornea its elasticity and how it's going to behave when we change its architecture. With the introduction of new imaging techniques, particularly Julian microscopy scanning, we then have the ability to measure the corneal elasticity, both overall and at individual points and at individual layers through the cornea. That data can then be put into a proper model, which is essentially a finite element model. And then with that, we can actually see what will happen when we do something to the cornea. So for the first time, we'll have proper weather forecasting based on true information. And then we'll be able to modify our treatments. Instead of having a generic treatment that is essentially FDA approved or CE marked in Europe, we'll be able to vary it based on incoming data. So just like we change our treatments based on sphere, cylinder and higher order aberrations, we'll be able to modify our treatments based on the biomechanics. And that will close the unpredictability gap just that little bit more. It will particularly have a big effect for incisional surgery. So when we talk about cataract surgery or femtosecond astigmatic corrections, intrastromal treatments, which are very much yet to come, then that's where biomechanics will make a big effect. It's been estimated that femtosecond intrastromal astigmatic incisions, 50% of the variability is individual biomechanics. So if we can close that, it doubles our predictability, and that transforms the procedure. The Excimer laser is a tool, and it's a gas laser currently. There have been solid-state lasers that are running at slightly different frequencies. They have different effects on the cornea. The Excimer itself at 193 nanometers as a gas laser could be improved with better beam control and so forth. And in particular, by having a wavefront sensor built into the laser system to measure the beam energy. So essentially what you do is you wavefront scan the laser optics. You can see the effect of the degradation of the mirrors, the optics, and even the absorption by ozone of the system and the chamber output. Each chamber has a fingerprint in terms of how the beam is when it comes out unsmoothed, and that fingerprint varies based on the actual chamber that's built, but also through its working life as it changes and evolves. So it's actually quite easy to wavefront scan that beam, and then you can measure the hot and cold spots and essentially then obviously change your pulse pattern to compensate for that. So you could clean up the Excimer laser. You could even take, for instance, 1 in 20 pulses, 1 in 50 pulses, and just do a null pulse onto your sensor and modify your treatment. That would clean it up dramatically. Smarter algorithms would make quite a considerable difference as well. We know that the cornea behaves at different levels at different depths, and at the present time that isn't really taken into account. And we also know that a pulse at the beginning results in a different ablation than a pulse at the end. So in terms of corneal dryness and so forth. So we could do a whole lot of things better. The drag on it is, quite frankly, regulatory. If you make a change in software or delivery, that means a full FDA reapplication, a full CE marking application. So you're looking at something like $30 million to make a software change. So essentially nothing happens. Time is frozen. Everybody's pushed into technological retirement because of that. And it's a difficult one because you have to have regulatory oversight for the protection of patients. On the other hand, too much oversight is essentially pushes everyone into what I've called technological retirement. Presbyopia has been described as the great frontier. And the reason for that is that you're trying to correct a dynamic situation that's been lost with something that's static. And a static correction doesn't truly make up for a dynamic. And also if you put a presbyopic increased depth of focus in the cornea, then the problem is with the aging lens, as well as the inability to flex and bend the lens, you also start getting increasing light scatter. And that scattering of the human lens reduces contrast. So if you have a multifocal cornea and you have some scatter of light, and you have the aging human lens, you have light scatter in the lens, and the two optical elements are separated apart 3 to 4 millimeters. So the reality is that you're not adding the scatter, you're squaring it. So the contrast on the retina is essentially the square root, and that's where people have problems. That's where the night vision issues come in. And so there are limitations to corneal multifocality. The corneal inlay is a very nice way of generating multifocality of a given amount. It's controllable. It can be placed into exactly where the surgeon needs it to be delivered. The delivery by Excimer laser has to be extremely precise. If you have a very small diameter optical element, then as you get to be a very small radius, then the number of microns becomes tiny, so the variation can be considerable, and its exact placement is critical. So the reality is that best optics is at the lens plane, and there's a clear need for a phakic lens for presbyopia. You're not trying to change sphere by any great extent. Cylinder is probably quite moderate to mild. So the reality is such a lens can be very thin, and it can generate the presbyopic enhanced depth of focus by a number of different optical methods. It's centered on the pupil, and therefore it's a very attractive way of multifocality. Also, it's removable. Of course, the much bigger deal is to do lens exchange, which is a good option. It's very popular, certainly in Europe, for hyperopia, where you don't have the risk of retinal detachment. But the problem is that once you have a lens implant and it's optic with current technology, you're stuck with 2017, 2018 technology. And there's going to be a revolution with lens implants once we have powered lenses. With the future polypneumatic optics, which change refractive index and requiring power, then when that comes in the mid to late 2020s, that will be a revolution with about 15 diopters of focus. And with an RFID chip, such that it's tunable from an external source, and also with biosensors implanted, such a lens is the lens that we all want in the future. We've of course seen Samsung's exploding phones, so lithium-ion batteries are untenable. Everyone's waiting for lithium air, which has 4 times the energy density, and you can also have solar energy picking up. Of course, the eye is designed to collect light. So there are a number of options that are being looked at, and patents that are in progress in this space. It's a heavily congested space, but these are the optics of the future. So those that are having implants today at a relatively young age will look enviously upon the implants of the future, and will be seeking an exchange, which is technically quite exacting to do. So these are the choices. We have to think not just of the present, but also for the future for the patient. And we can deliver optics now, but we can probably deliver even better optics in the future. It's an amazing specialty. The best is yet to come. And sight is 2/3 of the input to the human brain. It's 15% of the body's entire energy consumption. And it's up to us as refractive surgeons to make it as good as possible.